here we're going to have some more examples of Rust in production. I think this is, I see what this talks about. I think it's going to be absolutely fascinating. You're going to love it. And I think we should thank our speaker with even more gusto than usual, because as I understand it, Tristan's come over from Australia, and airport to airport was 25 hours, never mind everything else. So Tristan Lostroh, everyone.
Thank you. Today I'm going to be talking about our industrial-grade Internet of Things application, which is based on a milk tanker. So I am a software engineer at Clevy in Australia. Now I'm going to be honest, this isn't the view from my office, but it is just down the road. This is the Gold Coast. If you know Troy Hunt, that he comes from there. So we mainly do web marketing and web development using PHP. However, we do get the odd systems projects across the front desk. And our current project is Fridge Brain, which is a vaccine fridge with remote monitoring, and we're talking to all the fridge components. So the milk tank project was brought to us by an existing client for a completely different system. So this project is to replace an existing control system. So this system was fairly inflexible, so it couldn't deal with unusual situations like turning up to a farm in a different order, or having a new pickup turn up out of the blue. And it also depended on 2G. This is a problem in Australia as we turned off our 2G networks. And it also had a pretty basic keypad and LCD display like a pocket calculator, and it's definitely not user-friendly. So there's a couple of design considerations then that we had to take into account. So it had to be flexible. We had to allow pickups in any order. We actually used GPS to work out where we were, and so we automatically selected what farm we were at. And that also helped us minimise human input. So everyone knows that users can't be trusted. So if we can record as much automatically and take data from sensors, that's awesome. We needed to allow for future expansion. So there was a plan to have a link of the current fill status of the truck inside the cab, and we wanted to be able to add new sensors. So obviously network connectivity on a dairy farm, it's out in the country, it's not always that crash hot. It's even worse in Australia. So we needed to have reliable comms. We need to be able to make sure that the hardware and the software is stable, so that we're not sending out a tech at 4 o'clock in the morning. And another big thing that caught us out is that we needed to be, because the farmers are paid based on how much milk they are, we actually needed to be certified that the device was accurate. So that included temperatures, electrical, and vibration. Oddly enough, we had a vibration mount break, and that caused us a whole heap of issues. So there's two parts to our system. There's an interface board, which basically had the power supplies, sensor inputs, and the solenoid outputs, and the single board computer, which housed all the user interface. So our interface board here, we have our sensor solenoid outputs up the top, our sensor inputs and our microcontroller in the middle, and then the rest of the board is basically power supply, because truck 24 volts is definitely not clean. On our single board computer, we're actually using a Raspberry Pi compute module. We got lucky in that they released the compute module 3, so we have a nice quad-core processor, plenty of space to do everything we need to do. We have a 4G module here, so we don't have to worry about 2G we don't have to worry about the 4G network being turned off for a while. And we have 8 USB ports, HDMI port, and a SD card for some logging. So why Rust? Well, how do we pick Rust? So I actually came across one of Steve's release threads in /r/programming. I think it was V1, I'm not 100% sure. Looked interesting, basically filed it away for further use. And then this project sort of came up. So first thing we did was build an interface board emulator in C++ or C, one of the two. And I basically decided, yeah, I'm not a C++ programmer, so might do something else. So we built some prototypes out of using Rust, basically just proving all the crates that we wanted to use, making sure we could talk to a serial port, making sure we could draw stuff on the user interface. And, you know, they were fairly successful, and we basically then sat down, had a discussion, and we decided to use Rust. So now that the project's sort of wrapped up a bit and moving on to a different maintenance phase, were we successful? In my opinion, yes, absolutely. Basically, this is probably the most complex code I've ever written, and it's probably some of the highest quality I've ever written. Just to provide some stats, in our bug tracker, well, our issue tracker, we had about 100 bugs, about 200 features, and I haven't seen a project with that sort of percentages in our system, so I consider that pretty good. And the line of code ended up being around 20,000, which is on our systems is about a medium-sized project. So the main design of the single board computer is highly threaded. So we have a main thread which basically keeps the network and the logic threads alive. A couple of other things, making sure everything's hunky-dory. So the network basically, this is before request had async or has asynchronous commands. So we basically get the network to poll the database. If there's a new message, send it up, wait for a response, and sit around waiting for the next one. On the logic side, the logic is in charge of basically all these sub-threads, so making sure the graphics working, talking to the interface board, talking to GPS, and talking to our input devices like our RFID and barcode readers. And the logic obviously deals with all the logic of the program. So on our graphics, we basically had, because of my own limitations, we had to use a full-blown display manager. So certainly improvements could be made to bring that down, so we're only talking straight over HDMI port. So the main library we used is Conrod, and then basically to talk to all the threads we had used channels and enums. So this is the enum that we send to the graphics, and basically we have a couple of states, an are you alive and a terminate. So the basic, and then the states, then the response back from the graphics thread is are these. In this case, they are all buttons because because for Conrod, all the button logic is actually when you draw the button. So you had to have a way to get the buttons back from Conrod. So this is what the display actually looked like. So we have a couple of stats about the network and the GPS. This is the current status of the tanker. So in Australia, we can go all the way up to triples. So this, I think, is a B double. So and down here we have the current state of the route, how much they're expecting to load, who's logged on, what route they are, and where they are. And this is the current state of the tanker. In this case, the fill has been paused, so it's just waiting for a new command. This is what actually looks like in real life. If you ever get the chance to use an anodized aluminium case, coloured in a nice blue, do it. It looks great. So down the bottom we have some real physical buttons that light up. These actually map directly to the soft buttons on the touch screen. Here we have our RFID and barcode reader. It turns out thermal printers are a lot like UDP. You tell them to print and they may or may not. So this is what how we actually draw the user interface. So each screen basically has its own function. We pass down all the common elements to that. We tell it what the actual screen state is, and we give it some more information, what it needs to draw. So then each of the common elements have their own functions, and we pass down the information, and then finally we actually print the primitives to the screen. So actually talking to the hardware, each device basically got its own thread. It actually ended up being a lot easier to do this rather than use async I/O, mainly because we wanted to do a bit of pre-processing with the incoming serial data. So in this case, we are sending a command to the interface board, but first we have to convert it from the enum into a string representation. And we also get a string representation back. So this is where we convert our input from the interface board into an actual data structure that we understand. So we go through each of the temperature sensors, we convert it from a string into a 64-bit float, and then we push it back onto the vector. For the flow counter, they chose to use unsigned integer, free running, so we use this from string radix because it's a 16-bit number. Not entirely sure why they chose that, but there you go. So obviously the logic on these kinds of devices gets pretty complicated pretty quickly. The initial specification was fairly well detailed, but there was a fair chunk of scope creep. Like, I mean, as soon as you see that user interface, your mind just goes, oh, I can do this, this, and this now. Awesome. So basically, as much as possible, we made the logic completely asynchronous. So within the logic loop, it did not depend on something else happening directly before it. So there were plenty of timers that we had to use to wait for specific timeouts and for data to come back from the threads. So one small thing that I found dealing with a Rust project is that features obviously got put into trivial and not trivial, but the root, and particularly in PHP at least, non-trivial features can be extremely difficult to integrate with and make sure that they're reliable. What I found in Rust is that all the non-trivial features they just took longer to implement. They didn't actually increase the risk of the project at all. So that's probably something that we need to take note of going forward. And probably another point is that I didn't feel like there was much technical debt or much interest on the technical debt that needed to be paid, because obviously, if it compiles, it runs generally. Once you've implemented the feature, if it still builds, then it's probably implemented correctly. So this is an example of how the logic looks. It looks extremely complicated, and it is. However, it's basically all we're doing is we're stopping the low volume pump and we're starting the high volume pump. So we send the command to the interface board, which tells us which solenoids turn on and off. And then importantly, we also tell it what command we expect back from the interface board. So when we send a command to the interface board, we get a response, and we actually check that response and make sure it is the response we think it is. And then, yeah, this is where we look for the timer to make sure that make sure that the timer has actually expired before we start checking anything. So as we developed this program, I sort of felt that I exceeded the beginner level resources that we had, and I quickly found I was implementing new design patterns that I weren't really 100% sure if they were correct. So some of the issues that I found is that thread management, like retrying network connections, building user interfaces, talking to peripherals, and even simply accessing a particular element in a vector and having it aware of its neighbours. So like, we need to know what the previous one and the next one is. I sort of felt that the resources didn't cover these design patterns yet. So, and I actually sort of had an epiphany not long ago that every now and again the promoted crates topic comes up on Reddit, and how certain crates should be preferred among others. But another way of looking at it is maybe the design guide should look at, if you wanted to write a UI in this particular way, use Conrod. If you want to write it in a different way, use GDK. And so abstracting the crate, what crate to use and attach it to the problem might be a better way of dealing with both these design patterns and knowing which crates are good to use. And yeah, because, you know, design cred. So Clevy's next adventure in Rust is probably going to be FridgeBrain. So we're looking at version 2 being a fully customized board. I sort of feel that the Rust on bare metal is about where we were for Rust on the Raspberry Pi and when the Milk Tanker project. We were always cutting edge, but we weren't. We were unstable pretty quickly. We did start off at nightly because SerDes was only on nightly, but we moved to stable pretty quickly. A couple of issues that we know we need to solve first. So we definitely need over-the-air updates. I've sort of distilled this down into we basically need a bootloader where we can pick 1 or 2 different points for our main program. And the other thing we need to sort out is AT commands for the modem. It's sort of if anyone's aware of that, it's basically a serial port where you send them strings that generally start with AT and then get something back. And if you're lucky, you even you even talk to the internet and get a packet back. So that's about it from me. Thank you.
All right. Happy for questions? Yep. Yeah, okay, we've got a few minutes of questions. Anyone got any questions about shipping rusty crates on rusty shipping tankers, I guess? Okay, so the question was there an operating system on the Pi, or was the Pi running bare metal?
Yes, so we were running Raspbian. We did have a brief adventure into the Gumsticks modules using Ubuntu, but GPU support on those is mixed. However, but the Raspberry Pi had a half-decent OpenGL driver that actually made it work quite well.
Let's put our hands once together and thank Tristan.